In this problem, we're asked to find both an unknown mass and an unknown spring constant. If we hang the first mass onto this spring, it stretches the spring by 2 centimeters. If we add a second mass onto this, it stretches the spring an additional 4 centimeters. The second mass that we add is 2/10 of a kilogram, or 200 grams. So that gives us some critical pieces of information. It will be helpful here to draw in some of the forces that are acting. We have a force downward, which I will call force subcapital M. Is the force of gravity acting on that mass there. And the force acting up on that is the force of the spring as it's stretched in this first configuration, which I'll call F1. In this case, for the combined system, we have now force of gravity from the unknown mass and the force of gravity from the 200 grams, which I'll call F200, and a different spring force now, which is larger, which we'll call F2. So in these two particular cases, we have in the first, because this thing is at rest, we have F1 plus Fm is equal to 0. In this case over here, we similarly have Fm plus F200 plus F2 is equal to 0. Now, the force of the spring, F1 and F2, comes from Hooke's law, F is equal to minus kx. In this case, we don't know what the spring constant is, but let's write out what those positions are. So we have an F1 that is equal to minus kx1 and an F2 that's equal to minus kx2, where x1 is a downward displacement of 2 centimeters, so this is minus 0.02 meters, and x2 is equal to minus 0.06 meters. It's the sum of those two, 2 centimeters and 4 centimeters. So those are our two positions. Now we can simply take these two equations that we have right here and write them out and solve those simultaneously. So we have minus k x1 minus mg. That's this equation right over here, written out for the individual values. That must be equal to 0. And for this other one here, we have, so this comes from what I'll call my first equation here. And let's write the second one in a different color. So this second one here gives me minus kx2 minus mg minus mg again for this second mass, which is 0.2 kilograms times g, which I'm going to approximate as 10 meters per second squared, and that's equal to 0. And now we simply have to solve these simultaneously, and let's choose to subtract these two from one another. And if I do that, I'll find that subtracting this one here from this, I get k x1 minus x2. The mg's go away, and because I subtracted this, this becomes positive. This is plus 2 newtons, simply multiplying that through, and that's equal to 0. So this tells me then that I can solve for K as being minus 2 newtons over x2 minus x1, which is minus 2 newtons, over the difference in those, which is minus 0.04 meters. So the spring constant is 50 newtons per meter. So there's the first thing we needed to find. Now I can take this result here for the spring constant and plug it back into here and solve for my unknown mass. So I have K, which is 50, so 50 newtons per meter times x1, which we have right over here, minus 0.02 meters, is equal to big M times G. So I can find that mass. Notice the minus signs there cancel out. So I can find that mass as being this, 50 times 0.02, or 1 newton, divided by G, which again I will approximate as 10 meters per second squared. And I get 0.1 kilogram, or 100 grams. Now, if we had not been asked to find the spring constant as well, it would have been more expeditious to simply go through and use proportional reasoning. Since Hooke's law is linear, that means that the forces must be proportional to the displacements, and that meant that in this particular case the masses would also then be proportional. But since we needed to find K, we might as well go ahead and do it through this method.